temperature coefficient of reactivity for the moderator is, again, the change of the reactivity per degree centigrade, change of the moderator temperature per degree centigrade. And the reason is, again, for this mechanism we saw here, is responsible effect or process is the density. You see here the density of water as moderator as a function of temperature, and the higher the temperature, the lower is the density. Consequently, the scattering rate lower. Consequently, reduction of the reactivity. So we have discussed about that again here, and I said before too, because of this effect, you don't have this shape here, you would get the dashed line. Now, how the temperature could be determined, then here, in order to get it, we have to solve Fourier equation. That is like the same in neutron case. I said here is neutron current, but here is heat flux. Yeah. Heat flux, like we have here in neutron diffusion equation, we had neutron current or neutron flux. We have here heat flux. Here, change in temperature, derivation to X, Y, Z here. And the neutron diffusion equation was flux, derivation of the flux. There we had diffusion coefficient. Here we have conductivity because it is heat. And the other one, we say here conduction, heat conduction equation, or here Laplacian equation. It is similar to our diffusion equation. Here source term, because of fission. Here too, how much energy is produced, heat is produced because of the fission. And here the second derivation of here temperature, there was flux, and here again the conductivity. So this can be, if you solve the heat conduction equation, like in neutron flux or diffusion equation, you would get the temperature shape here, like in the center high, rod, and at the boundaries, of course, lower. And there is one additional relationship. Here is the solution, you remember, and then you get here, again, temperature maximum, that means in the center, maximum at the outer boundary, that means here, the difference here depends on the radius of the pellet, fuel pellet in this case. So, but this, everything describes the temperature profile in the rod. But what about the temperature in the coolant? It is then obtained by applying heat transfer relationship. And this is like this one here. This is coolant temperature. This is surface temperature of the solid material, for example, rod. And the bigger the difference, the higher is the heat flux from the solid area to the coolant. And the H here is called heat transfer coefficient based on empirical correlations. So, I'm not going to repeat it again, but anyhow, you can determine here exactly how the temperature increase takes place from the bottom, from the inlet, for example, of a channel to the upper part of the cooling channel. Because at every segment here, heat is transferred from the rod, red area, to the coolant, and the hot water goes as inlet to the next segment and heated up again, so that at the end, the temperature would be changing from inlet to the outlet by a big amount of value here. And you see here, again, the relationship here, temperature change because of the mass flow depends on the mass flow here. The higher the mass flow, the less is, of course, the temperature increase. So heat capacity, and this is the temperature increase inside one segment here. For example, from here to here, or the channel from here to here, or from here to here. And you see here, is proportional or given by heat flux from the rod to the coolant. Depends on the position, because heat flux depends on the power production. And remember, flux distribution in the center is highest value, at the boundaries, upper boundary, lower boundary, lower. So for this reason, you have a cosine function. By solving this one, the step by step, then we get connected to the other value, or other solution, that is heat convection equation. You get then how big is the temperature profile for the coolant from the bottom to the top. Okay, so good. Now, I said during the last lecture too that Soltron is a multi-purpose code or package. It can be applied not only for reactivity incident, it can be applied for heat transfer phenomena and processes, and for mass flow, pumping failure, for example, different cases. For this reason, it should be then applied for that type of cases. I would like then to stop here the presentation, and today I told to you too, we are going to use Soltron code for two different packages. Package one for neutron kinetic, and package two is then reactor dynamics. And very well-defined questions are here, and the answer to these questions then should be produced or given by Soltron application. So, and so I would like to show you then right here. So the file is not open. First, I have okay, yeah. So I hope you see First point is I would like to explain what the work is. Here again, the workshop or simulation session today, and we should then answer or try to simulate or to apply Soltran code and find the answer to these questions. That is the first question, part one. Using the program, I hope you see it. Using the program Soltran, study the change of the reactor power and neutron flux, that means proportional to each other, no feedback effect for the following reactivity insertions: 0.1, 0.4, 0.7, and -1% decay to K. You remember what the unit is. So, good. And then determine for every case the stable reactor period. You remember the procedure? The reactor period, and compare it with the result of analytical solution. So, regarding the analytical solution, one point is, you remember this diagram? We saw today too, and this diagram. So, if you run it, if you take, for example, 0.1% case, then it means you take here this value here, reactivity 10 minus 3, because the unit here for reactivity is absolute value. But in the question, it was 0.1% delta K to K. That means 0.1 is equal in absolute unit is 0.10 power minus 3, that value. And then you go here, positive reactivity, you can read down how big the reactor period is. And one can compare this one with very precise solution or a correct solution by Soltran. That is one comparison. The other one is you take the general analytical solution we discussed before. You remember this formula? So this formula, you see here, that is the stable reactor period. Inverse of this ratio here is reactor period. So, and that is two ways. Again, from graphic and from this relationship. For example, in case of 0.1%, you need only to put for rho 0.001, and beta is available there, lambda is available there, and you can calculate. Good. And for the other case, exactly given in this example, is similar. There are other values, so similar. And then the second part is, second question is calculate the reactor's behavior. Now, dynamics. Power temperatures. For reactivity insertion, 0.4% and 0.7% under the consideration of feedback effect dynamics. So, and in this case, again, we run Fortran code, but there is one line inside the input file describing the reactivity feedback effect. One is the temperature coefficient of reactivity for the fuel, and the other one is for the moderator. For the reactor kinetic, these two numbers are put 0. But in case of this case, session 2, it should be containing real number or correct numbers. And you would then get it. If we do that job, I would like then to tell how big the two numbers are. Good. Yeah. And the point is, after doing the individual jobs here, then at the end, not here today, you should make at home then a very short report on your study on neutron kinetic and reactor dynamics. So, and here probably I can show you how a short report looks like. Here, I hope I find it. So, for example, here, I hope you see it. So, you see here, that is the similar case. You remember the same diagram in order to take the theoretical value and compare with the simulation results regarding reactor period. So exercises, here's the case 1, and you see here graphics of the reactor power of logs for 0.1, and here is the time, and here is the reactor power. How do you get the reactor power? In order to make a plot here, I would like then to explain what the way is, because you have on your folder, which was sent to you, there is one additional plotting routine, and you can take the result of the Fortran calculation or simulation, and using that plot routines, we can produce such graphs, and then we can determine for here, according to the formula, remember here, the formula here, according to this formula, you can determine the reactor period, stable reactor period, and then again compare with theoretical, two theoretical ways. Good. So now I hope everybody could download the folder I sent to you. So it looks like, you remember that was this type of email was sent to you. You remember? And this email attached was a folder . So the point is, now this folder is available on your email. Good. And I said what to do. The way is, you should first open your email and then download this 7-zip data file or folder. So if you download it, maybe it would be placed in your download list, or you can download it as 7Z folder in any folder of your own. So after doing that one, so you can then there unpack it. Because in this case, packed case is not applicable. First, you have unpack it. Unpack using right hand here mouse, and then there would be then a command using and saying, yes, it should be unpacked in your own folder. And if you do that, then a new folder would be appearing with the same name, but instead of 7Z, it would be only a folder, and you can open it as a very common, very normal folder. Like here, I can show you what happens if you unpack it. Where is that? So if you unpack it, you would get, and I said, a very normal common folder here called Soltran Online. It was the name of the packed folder. So it's the same. Then you can open this one. So if I open it, no. You see here, I hope you see it, what I'm doing. Otherwise, no, you don't see it. Now you should see it. Again, going back, see, after unpacking it, you get a folder, the same folder, but not 7Z, but a normal, right? Here called Soltran Online. And if you click on it, you can open it and you see individual data files in this one, but now unpacked. And you find everything in this folder. For example, executable program. Here, you see Soltran dot exe executable. So I hope you see that one. Please do this job. That means we should have the same stages. That means you should have on your screen exactly this folder, Soltran Online, folder opened like my folder here you see on screen. Please give me a response or signal that you have it. Okay? Thank you. And I'm waiting. Nobody more? Thank you. Thank you. And please more. Please more. Okay. Very good. More. Please. Yes, thank you. More. Thank you. Thank you. I'm not sure everybody has it or only parts. If somebody haven't it, please give a short response. It seems to be okay. Again, it is very important because I said, after doing these simulations, you have to write a small report I showed you before. And for this reason, it is important that we start the application together. So, can I say everybody has it? Or opened it? It means you see these files on in your folder. Good. Now, the point is, if you, for example, click on or first select Sotran X. I don't know if it, in your cases in German is Anwendung, application. That is X file, executable file. So if you click on that, like myself, or so you get a new screen. You get a new screen. I hope you see it. So that is the new screen. It is coming from Sultran News, and it says, give the name of the input file. Input file means all information, case description is included in that input file. And input file is, in this case, is, for example, you see sim 0.4 .inp input, because it is called so. You see, if you look to this data file, it is called INP input. Enter. So now it asks you, how should I call the output file? The results with table, power, and everything. We say everybody can take the initials of his names. For example, I say NA1 out. It means output. No. Then this black screen would be disappearing, and you get the results. You see here in your folder, in my case was NA1. Did you get one too in your case?
Professor, sorry?
Yeah, please.
One of your students is waiting for a quarter hour for you to let him in. Can you please let him in?
Moment. One student. Oh, sorry. Ah, yes. I didn't see it. Sorry. Oh, okay. Good. You see, everybody get one output file, correct? And this output file is the result of the simulation using the input file sim 0.4. And I open this file, that's output file. So you see, that is the output file. I hope you see it. See, that is exactly the output file. You have. Do you agree with me? Did you get this output? No, sorry, that is the input file. This is the output file. You see, you would get such an output. You can open your own output. The structure is exactly the same. And you can see here very clearly the first box, red box here, is reactor kinetic parameters. We have given or defined in the input file. For example, number of the delayed neutrons, neutron lifetimes here, and total beta, initial power, how long the reactor has been operated during the steady state condition, and what is the time step for solving the numerical solution. What is the end time or T end? That means the simulation should be done here for 200 seconds only. So, and the big table at the bottom, you see time, and you see power. That is exactly power at every time step. You see, it is normalized to 1. That means if the power is 2000 megawatt, then every value has to be multiplied by that number. And so it shows here very clearly an increase because of the reactivity insertion. See here? And one column here says row 1. I hope you see it. Row 1, see here? In this case, in my output, it is 0.4%. But the first exercise, the first question, which has to be analyzed by yourself, is 0.1. That means it should be, again, 0.1% delta K to K. Good. You see here very clearly. So, row 1, you see this column here. And then I go back to the third column, power D. This is decay heat power. I said before, because we produce fission product, precursors, like the source for delayed neutrons, so they produce power too. And this is the fraction of the delayed decay heat is in this case, 0.6%. So, and then the next column is flow rate, normalized to 1. Doesn't matter because it has to be multiplied with the initial value. So, T inlet, you remember inlet temperature, that is 59 degrees centigrade, and it has remained constant. So, T out, that is the temperature of the coolant at the outlet. So, you remember the numerical solution, the temperature would be increasing because the power is increasing. And you see here at the time step, steady state, 63.5, but it is going higher and higher. So, and the next column, temperature fuel, solid material, fuel. So, consisting of uranium-235 and uranium-238, for example. It is the first time point 0 at 105 degrees centigrade, but it goes higher too, because I said, because of the second column, power is going on, off. So, and then you see the next column is reactivity, inserted reactivity. And the second one is reactivity feedback. Normally it is negative because temperature goes higher, reactivity contribution because of the temperature increase is negative. But here is 0 because in this case we make only reactor neutron kinetic, no feedback. We put in the input the temperature coefficient of reactivity for moderator and fuel 0. You remember, you see here too. You see here, this is this line. coefficient of reactivity, Doppler moderator, is practically zero, e power minus 43. That means zero. For this reason, there is no feedback and no feedback reactivity for rho 2. And the next column, that means rho, not rho 1 and rho 2, rho is the total net reactivity. And you see here, net reactivity is exactly the same like the first one, because there is no feedback. Good. That is all what we need. Okay? Good. Now we go, that is the output. So if you look again to your folders with all individual files, so you see here, I said before too, sim 0.4 is an input file. You can open on your own computer. So that's exactly the input file. So So the input file, sim4, looks like this. Oh, you see here the first lines. The first two lines are only for information. You can put here any text you want. So, and for example, this input in your case is for reactivity 0.4. And exactly this 0.4 is at the bottom. You see here, the red box at the bottom, and here you see here 0.16, but in your case should be 0.1. That means for the first case you want to simulate, you calculate, then this table should be changed, or you should make from 0.16, or in my case, or in your case is probably your input is 0.4. You should put the 0.1, first case, everything. All values should be equal to 0.1. Understand what I mean? So, for this reason, in the first line and second line, we put here information what case is going to be simulated. And here's additional information, LP, that means here prompt neutral lifetime is 10 minus 3. But your calculations, that means simulation sheet, case 1, it should be 10 power minus 4 instead of power minus 3. Okay? Good. Now, the next line, I explained last time too, here starting with 500, it is how many time intervals, time step should be considered for this simulation. That means the whole range. It is, for example, if it is for 200, then it would be divided in small segments. So the next one is the heat capacity. Remember, this is for kinetic is not important, but for dynamic, yes. Heat capacity coolant. You shouldn't change it. Heat capacity fuel. Mass fuel, MF. Mass coolant. Heat transfer coefficient. Do you remember? Newton cooling formula. There was heat flux from this rod, solid material, to the coolant was H multiplied by Ts minus T coolant. Exactly, this is the heat transfer coefficient.
Yeah, brother.
H there. Area. How big is the total area? Because the heat transfer coefficient is for 1 square centimeter, but the total area should be considered. That is total area. So the next one, T start, is not very relevant to you, but maybe afterwards I can explain. Again, that is not very relevant for you. It is only the time delay in any contraction for the control of the reactivity accident or any accident. Time delay in the contraction. So then the next red box, that is very simple, 6 delayed neutron groups, lifetime, prompt neutron lifetime, please change it to 10 power minus 4 in your case. Feedback effect is not known for the neutron kinetic, practically zero, but in case of reactive dynamic, you should remove, the numbers are correct, you should remove from here, instead of 43, put for the first value only minus 4, and for the next one, minus E minus 3. First one again, E minus 4, second one, E minus 3. Okay. Velocity, coolant, mass flow, and so on. Pressure is important of the coolant. You shouldn't change it because it is not a coolant transient. Mass flow, 460 kilogram per second. That is not important, and you can keep it as it is. Heat exchanger temperature. So, and secondary side, coolant mass, 5,000, how much it is. So, and then heating area, thickness of the plates, heat exchanger plates, and temperature at the outside. Primary side, secondary side. So now you go to to a box, red box, you see here power, 20. Don't change it because power increase is based on normalized value. So the next one is operating time during the steady state condition. Here is something, you can put any number there, 1 day, 30 days, or 1 year, for neutron kinetic and so on. It doesn't have any effect. Rho means reactivity during the or at the end of steady state conditions. So still steady state condition, but at the end is zero. Imaginable because steady step. Time step, you remember? The whole range simulation time has to be divided in individual steps, time step. That is the every individual intervals in seconds. So time end, that means simulation should be finished, should be ended at 200 seconds. And because you produce, you can imagine here how many lines you would produce. For this reason, it says print. It means only print out only every 100 steps. So the next one is again for more pumping transient, flow transient. It says steady state condition, 460 kilogram per second, which is for you not important. T inlet temperature 59 degree into the core, into the fuel elements. And then next one is for, I said before too, you can simulate with this package, with this code, the flow transient too. That means mass flow goes down or goes higher, and because of the malfunction of the pumps, for example. And here, for during the whole simulation time, up to 200 seconds, here is mass flow every time the same, because we don't simulate here flow transient. Next one, for regarding the temperature transient, could be something. It could be something happens with the heat exchanger. So that means secondary pumps wouldn't be working. The temperature from the secondary side would be increasing. Consequently, the primary side would be changing. This can be simulated or modeled by the temperature increase at the inlet. But that is again not the case. We are going to simulate. For this reason, at zero is inlet temperature 59. At the end time, 200 seconds. The second is the same value. For this reason, not important. Important is, again, coming back to the simulation sheet, your case, this box, red box at the bottom, you see here is the inserted reactivity for different time steps. It is a table. It is very arbitrary. You can take here only two lines, one for 0 and the other one for 200. Doesn't matter. But the important is at the time point 0, you have still steady state, is reactivity 0, and immediately after this time point, after 0, that means 0.01 seconds later, we have a jump in the reactivity. It is 0.4, and in our case, in this case, is 0.16. So you should, for the first case, put there 0.1. The right-hand side table here, SCRAM table, is not very relevant to you. That is important if you want to study the safety effect of a reactor. That means reactivity accident has been taken place, happened, and then what is about the reaction or counteraction, reaction of the shutdown system, of safety system. The safety system can be here modeled by an additional table describing the reactivity effect of the safety system for the same time table. So, but here for the reactivity should be put only the negative reactivity of the shutdown system. So, and you see here, then everything is constant, here 0.1 in your case, in your first case. I hope it is very clear, this input. What you have only to change is the table at the bottom. The first case, only 0.1 everywhere here. Okay? Now, we go to the next one. If you have any question, please ask me, because you are going to run it and then produce a report on that. So, for this reason, I would like to say, please take your input. For example, or first make a copy of it, rename it to sim 0.1. Copied one. Sim 0.1. Good. And then open it, please. Open it, please. And you see such a table, such an input. First change, please change live time. Instead of 3, please 4. Typical PWR. Instead of -3, -4. Then please jump to the bottom. So, I don't know what numbers you find at the bottom. Please change all numbers you find there in the second column, all numbers to 0.10 or 0.1000. All numbers. So you see, that is the copy of my 0.4 input. I change it to sim 0.1. Okay, now we can open it. So you find here, I said before too, only one thing can be changed here. That is the line. Unfortunately, I cannot take my laser pointer here. Editor doesn't allow it.
Snabi, we can see nothing. It's gray.
Moment. Maybe I can give it free here again, probably. Do you see it?
Yes, thank you.
Yeah, okay. But you don't see my cursor, I guess. So, again, go to the line. You see here, that is first two, line 7, you see, number, neutrons, 6, and lifetime. Put there 10e minus 4, if it is not the case. Then jump to the bottom row. You see accident table. In this opened file, it is 0.4. Now we can make only one, your case, one. I can do it in one step, but in order not to have any problem, one. Okay. Yeah. Now you can go to the top of the screen, left-hand side, save. Please don't save it under a new name. Just take here only the sign, the symbol, and save it, because you have renamed it before. So, okay? Now we can leave the input file. Okay? And go to the folder again. I hope you see it. In your folder, and you find there SIM 0.1 IMP. Now you can jump again to Sotran executable and click on it. Look, you get this new screen. I hope you see it. Now you can, it says input. You have generated the new input with the name SIM 0.1 IMP. Now output file. So you can take your initial and numbering. For example, in my case, I say NA 0.1. Dot out. No. See, the output file appears here. I hope you have it too. Somebody asked, is the lifetime 10e minus 4 correct? Moore or Mr. Moore. Not, it is not correct. 10e minus 4 not correct. It should be 1 point e minus 4. Good. If you have your output file, please open it. Mrs. Becker, I guess you ask 3.3 minus 4 is correct? No, that should be for now, for kinetic, neutron kinetic. You should leave it as it is. That means it should be, for now, should be E minus 43. And two values should be minus 43. The second value, 43 too. Not E minus 4. That is for, yeah, thank you. Okay. I'm sorry, very sorry for that. Good. Now, if everybody is ready to open the output file, so it is the same case. I hope you see it. I opened my file too. You can open yours. You see it, right? Well, that is my case. That is practically your case. And you see here, the first block is, again, the input data values, data you have input in your input file. You don't need to talk about values, but important is here, again, in the middle, something you see dt, that means delta t, time intervals, 0.005, and t end, you see 200 seconds. So, and the big table at the bottom, time, power, body, we talked about that. So, good. And you see in the column, the third one from the right-hand side. no, the fourth one. You see everywhere 0.1. 0.1. That means that is the reactivity you have inserted that you want to simulate or to study. So, and first column is time in second. Second one is power again. It is increasing, slowly increasing. If you go lower and lower, you find values increasing. So, there is one text line so if you look to your output after the line with the time 46, there is one text line. It says critical heat flux exceeded the burnout value because the power is 3.4 times higher than the initial value. That is only for information. It said it has information. Please remove this text line. Please remove it or delete it. I do too. Now, that is exactly what you should do. That means power as a function of the time should be plotted. Here, first, because I removed or deleted one line, I have to save it again. No, good. Now, please go back to your folder. Do you see there, I hope you see, diagram desktop. Do you see it? So, diagram, you see here, diagram desktop. This diagram allows you to plot any table. That is a plotting routine or program. So, please look, that is important. Otherwise, you cannot plot the result of your simulations. So, you remember, like in other report, here in this report, you see here, power as a function of time. So this can be plotted by that routine. You don't need any additional program for it. So you go, click on it. You see, you get a warning. It says something cannot be opened. Please ignore this information. Please ignore this information. You can say, okay, so, but you can say, okay, and then a new screen you find here, and this is for plotting instruction. What data file you want to plot? You can put here the name of, for example, what was it? It was, I don't know how you named it. So, in my case was NA 0.1 out. I can put this name here, or I can take here the bottom in the middle. It says search for data file. If you say,
Professor, we are just seeing green box for the plotting program.
Moment, then I have to give it free. Moment. But it is active. You don't see it? Do you see it?
Now, yes.
So, please, if you click on Diagram Desktop, you get a very small screen or window screen. Say, okay. Then you would get this window here, or this screen here. Yeah? Okay? And again, here, there's a small box here for data file. You can put here the name of your data output file you have produced. Or you can take here search in the middle. You see here, it is in German, but you can take here search. No. You see that your folder appears here. For example, Soltron Online, yes, that is folder, here. What is it? So, here. So, did you find your output and say it would be copied in this box, my output file? Yeah? Do you have it? Okay. Then say, okay. Oh, Now a new window or a screen you would get, and this screen contains your output. Now we want to make a plot. You need first to select what column against what column. X value axis is the first one type. I am interested in number 2, column number 2 power, only that one. I can take the other ones too. For example, view. That would be 1, 2, 3, 4, 5, 6, 7. But it is better on first to make only for power. So then you see here there is one additional box. It says what column should be taken for x-axis. Here at the right-hand side, you see 1. I hope, sorry, maybe you don't see it. So, do you see that is then, I hope you have it. If you have selected your data file in that screen and then say, okay, then this screen would be appearing on your computer. So then that means your output file. And first step is, again, you see here at the top the name of the output file. Then what columns or which columns should be used. The first one has x-axis, the second one here highlighted, second one would be then power, I am interested in. So, and then at the end of this box, the series, you find here what column is X again, is 1, and you can put here, here's the X-axis for shifting and so on. Important, but now here at the bottom right-hand side, you see title. You can put any title. Case 0.1, reactivity, kinetic, or so on. And you can here put for description of the x-axis, you can put here time, second, and y-axis, relative flux or relative power, depends on you. And then you can say, now, before saying next step, weiter, next step, first, you have to select which part of your table should be plotted. In order to do this, we have to highlight it. And then, you see, you go to the first line, at the bottom of time, only numbers, and highlight it. I hope you see it in my case. So, highlighted. No. For example, so if you have highlighted it, that means that is the part of my table which has to be plotted. But be careful, no text should be inside the plotted block or inside the here highlighted block. So, and then you say weiter, that means next step. No. You see? I hope you see in my case. Maybe you don't see, I can make it free. Oh, do you see it? Oh. Oh, you see it. That is plot of our results. And we didn't define any title for y-axis, any title for x-axis, but everything can be. No, we can make three-dimensional too, something like three-dimensional, like here, for example. So, that would be then the power against time. So you can calculate here then reactive period. In order to make the reactive period, you remember, we had one example, you take 2 times, for example, at 25 and 35, and read down the corresponding value for power or flux from y-axis. Use the formula, remember, delta T divided logarithm of the ratio of the fluxes. Then you have the period. Okay? So exactly this job should be done by yourself. And you remember, in case of this report somebody made in the past, the same, for a long time. So he or she took 2 times here and 2 powers, calculated according to that formula the reactive period. And analytical, that would be result of the simulation, of course. If you, for the analytical one, I said before in the beginning, you take the formula in your material, in lecture material, you remember formula, analytical solution, that is one theoretical, and the other one is according to the diagram, the green one, you remember? Somewhere, but you know what I mean. Oh, here, that one. From here, I hope you see it. From here, you can, what reactivity we have? Reactivity was 0.1%. Absolute means 0.001. That means it would be something like this here. You see at the x-axis, this value going to the top, reading down on the y-axis. That would be your period. Something like here, 45 or something like this. But you should read down precisely. Good. I hope it is clear now. So, any question?
I got a question because when I wanted to plot the diagram, it just says that my program is not functioning. It has keine Rückmeldung mehr and just resets.
Mm-hmm. no reaction from your system.
Correct.
Yeah, maybe the reason is it didn't find your output file. You should then first take search the bottom and the middle, sie durchsuchen.
Oh, I got the file, but when I want to, after I marked all the data, I want to do the plots of the graph, it doesn't work.
Look, if maybe your output file doesn't contain any values. Look at it.
No, it's the normal file. It has values.
So, did you delete the text line?
Yes.
Can you give your screen?
Yes, I can share my screen. 1 second. Oh. It just closed on itself. 1 second.
Moment. But unfortunately, I don't see anything.
Yeah, I have to reload the file.
Yeah. Is that yours?
Yes.
No.
When I click on, oh, no, it's worked.
It works.
Yeah, but before that, it's just said keine Rückmeldung.
Okay. Then it's okay. The problem has been solved. Good. Very good. So, any further questions? Everybody is expert in application?
Maybe I have a short question.
Yeah, please.
I was just curious because, well, in the input file, we just said that we have a reactivity of 0.1 put there, but in the output file, then if you look, it just says 0.1 E minus 1%.
Output file.
Yeah, so...
Yeah, don't worry about that because it is not a mistake in the output or file, but it divides by itself by 10. That means if you find there 0.1 E minus 1, it means exactly 0.1. It is something inside the program.
Okay, so the important thing is what we just write in the input file.
Yes, exactly. You should be careful. Only take that value which you have in your input file.
Okay, and
the number at the output is the same number but divided by 10.
Okay, and then for the report, we'll just try to get results for these 5 reactivities you have given here.
Yeah, for your report, then the power is okay. If you want to make a plot, then your y-axis is power, it is correct. And x-axis is the first column, the time is correct too. And you calculate the reactor period only taking the power. And the other values, other columns, you don't need.
Okay, and what is then the further plan with our report? So I guess we should try that on our own at home.
The report, yes, you can try to run all cases now, and you could use the output files today and take the output files with you and make then plots and writing, I said, a short report. Because the first case takes time, only 0.1 case takes time. All others are very similar.
What do you mean with it takes time? So it takes time
because
to...
we have discussed many minutes or long time of the case. But the next one, we don't need to talk about it because it is practically the same, only the number is different.
Yeah, okay, but what is our task then? So we should write the report until next week, or...
Yeah, it would be better if you could deliver then next week, by latest or next week.
So is it part of our exam then? So do we get a grade on this, or should we just...
Yes, but not big part of your mark. Exams mark, only a fraction.
Okay, and then we should also answer the second question.
Part 2.
Or do we discuss this later?
Yeah, we are going to discuss about that too. If you know exactly, if you have produced the cases, neutron kinetic cases, that means part 1. For all individual values, 0.1, 0.4, 0.7, and minus 0.4, this is just only a run. So then we go to the second part and we run it together.
So okay. So this is the plan now for next week, or
No, today.
Or okay, so we just carry on with it. Okay.
Yeah. For this reason, I said the first case, 0.1, took more time. The others are only repeating. Again, I hope you see this file. Oh. I hope you hear me, or something happened here. Okay. So I hope you see this diagram here. Yours should be similar. You see here, again, the case 0.1, for slightly different values. Neutronic data are, in this case, slightly different, but yours is similar. So you see, you should produce such a plot, relative power, that means second column, and as a function of time, in this case is up to 30 seconds. And from this curve, you can read down your reactor period. So, and I said, theoretical calculation is well known. Second case should be similar, but only the value is different. That means 0.4. That is for other reactor, but for your case is similar to that. Again, here, power, relative power as a function of time for 30 seconds. But by reading down the reactor period, you should be careful. The later the time points, the better is the result, because we need stable condition. So, see here, the time point is 10 and 100. That is later. No. This is the case 0.7%. You should be very careful. This value is a very big number, 0.7%. That means that your reactor gets supercritical. Supercritical because this reactivity insertion is bigger than the contribution of the delayed neutrons. Practically, the reactor is not controllable. For this reason, you see here a jump to very high values. But anyhow, you can determine it. So, and the calculation can be done only up to 9 seconds or 10 seconds because the power goes, you see, on the y-axis, 10 power 33. So it is critical, super critical. So, So if you have any problem with plotting, then with respect to time range and so on, one helpful step is in the input file. I hope. So that is the input file. I hope you have it. So you see, that is your input file for the case 0.1. You remember at the bottom. No. It could be that you have some problem with plotting in other cases, case 0.4 or 0.7 and so on. The plotting problem, that means for better resolution, for example, you have the possibility to change the time steps. But time step here, you see in the middle, time step 0.005. You can keep it, but the end time can be reduced. For example, in case of high reactivity insertion, you don't need, it is impossible to calculate so long time because the reactor power goes to very, very high values. But partly you can then, by checking these numbers, you can print every 10 steps or after every 10 steps or after every steps. You can control it, your output or your plot, by the variation of these numbers too. It is additional tools in optimization of your plots. So again, I would like to plot it. So that is again the first case you had before. So that is exactly the same case, 0.1 case, but for short time, is from 0 only to 4 seconds, you see on the x-axis. And you can make here, again, 3D representation too. Depends, at the bottom you see here 3D or orthogonal, depends how you want to have it. So, and then on this page, you see at the left-hand side bottom, you see here, save to file. You can save your plot to a separate file, plot file, image. And then you can use it, copy it in your report if you want. Depends on you. Sure. Good. If everything is okay, if you don't have any questions and you can run all cases, then we can jump to the part 2, reactor dynamics. So, are you ready for the next part? Or should we try to calculate the last case neutron kinetic, 0.7? That is very simple case. Again, first you take one of your input file, for example, sim 0.1, first rename it, to, for example, 0.7. Then open it, or first copy it to 0.7. And then open it, and at the bottom replace all values. Replace all values here, 0.1 to 0.7. You can do in one step of find and change or find and replace, like here. So, then you save it here at the top left, not with a new name. And you can run it, it's no problem. Go to your folder. Now go to folder and take Zotran. So it asks you again to your input, sim 0.7.imp, so output and R 0.7, out, so here's the input. That one, hope you see it. So that is the output file. You see here for at the column first line again time, and the next one is the row is here 0.7, as you see at row 1. It gives you exactly the reactivity insert. But please don't forget, in case of plotting, take this type of text lines, critical heat flux exceeded, or any text line inside your table should be then deleted. Otherwise, you cannot highlight and then plot it. So, good. And here, one thing is important because in this case, reactivity, inserted reactivity is big. I said supercritical reactor. For this reason, you see only going from 0 times 0 to only 0.05 seconds later, or 0.1 second later, the reactor power gets 10 times higher. And after only 0.5 seconds, you get 329 times higher. That means it is very fast increase, supercritical. For this reason, in order to get better representation, it is better to take here than the number of the print very small, not every 100 or every 10 or every, in order to get better resolution here. Okay, I guess everything is, then you need only, see here in this table, after 9.5 seconds, the power gets 0.16 e power 34. Very big numbers. I said supercritical, not controllable. After this factor, you don't get any values more. That means it is very big and then no number can be calculated. For this reason, I said before, it should be calculated and for short period. And you remember, there was calculation up to 5 seconds or 6 seconds, and you can determine the reactive period. And reactive period in this case is similar to the value we calculated we discussed during the lecture, similar to critical case. That means practically the same, like you neglect the delayed neutrons. You remember? Good. If you agree now, or everything with neutron kinetic is very clear, you can produce data file and plots and so on, then we jump to the next session or next part, and then we discuss one case, and the other cases should be then similar. So one point is, this case. So I hope you see it again. That is the second one. Session 2, calculate the reactor behavior. Now, power temperatures for reactivity insertion 0.4% and 0.7%. That means in that case would be supercritical under the consideration of feedback effect, reactor dynamics. That is the question. And 0.4%, that one, has been calculated for neutron kinetic. That means neglecting the feedback factors. You remember? And you take for this case your same input file. Do you remember input file? Input file is 0.4. I hope you see it. So that is your input file. Here, 0.4. 4. First, rename it, because now is dynamic part. No, we call it 0.4, sim 0.4 minus dy, dynamic. So only that. Or maybe it is better first to copy it in order to keep the kinetic one. First copy, and then insert. See, that is the copy now. And this copy should be renamed to dy, dynamic. Now, if you have this frame, then you open it. Now you should look to this input file for dynamic case. And then shade it as you know. So I hope this is that one. You see? At the bottom of this file, you see your number 0.4 everywhere. But at the top, everything remains the same. No change, but you see 6th or 7th line here, feedback. So 2 numbers. The first one is for fuel effect, Doppler coefficient, or reactivity coefficient for fuel temperature, and the second one is for moderator. I said before too that the correct value is, for reactor dynamic, this is -4, the first one. The second one is E -3. So, do you see it? Now is the feedback effect would be effective. Okay? Nothing more. Only this one should be changed. Back to dynamic. So, and then save it at the top. So, and then we go to your folder is available here, the new or dynamic case. You run it, so it's run, exafoil. So it says you have it. So again, I share it with you here. See, now input, say, sim 0.4 minus dy INP. Oh. Then here the same, sim 0. minus dy minus out. Okay. Is there, something happened? Something happened? No, it's correct. So you see this data file? You can open it. So I hope you see the output file. So the output file for 0.7 dynamic. Everything is at the top, okay? And you see in the first, second, third, fourth, 5, 6, 7th line, coefficient of reactivity, Doppler and moderator, Doppler fuel. You see, correct numbers, minus, everything is minus because it reduces the reactivity. -4 and power -3. Correct numbers. Good. The table you see at the bottom, you're familiar with it, and you see here time, power, and flow is constant. You don't need it. The inlet temperature is constant, 59. Outlet temperature changing, would be changing. Fuel temperature would be changing too. And finally, you see here now sorry, and you see here the column before the last one, raw net value. Raw net value, you see, it is not more the same like we have inserted, not more 0.4. It is less because of the effect of the temperature. The temperature increase, fuel moderator, reduces the inserted reactivity. And the last RHO is the net reactivity at every time step. So that would be the values. So the consequence is the power wouldn't be changing so like we had in neutron kinetic case. You see here, the increase is more moderate, not so fast like without feedback. So, and it can be then calculated here. And you see here, fuel temperature too, and so on, can be calculated. Okay? Fuel temperature and so on. And output, you should keep the output for plotting. So plotting, no problem. And in your plot routines, you can specify many lines or many columns. Or you can select column 1, we have for power was column 2. We can take, for example, column 7 for fuel, or column 6 for moderator temperature, and so on. So that means something like similar to this case you would be producing. That is kinetic. The negative case. Session 2. You see here power for 0.4 case, but other nuclear data. Then we have some oscillation in power here. I hope you see it. Yeah, but the increase of the reactor power is limited. You get some stabilization here. It gets stabilized because of the temperature feedback, not continuously increasing. So in this case, temperature of the moderator, for example, you see it goes higher from the initial value, increasing up to a given value. If the boiling temperature has been reached, and it would be started, or the power increase, if the power increase due to the net reactivity stopped, then the temperature of the coolant wouldn't be further increasing. And in case of the temperature of the fuel, similar situation, you see first increasing up to a given value. After it, because the thickness of this curve is very big due to the oscillation. From one step to other step, the temperature goes, or the reactivity goes down, and then power goes down too, because of the feedback effect, and the temperature goes down. And because the temperature goes down in one step, the reactivity increases, power increases, and temperature goes higher. Again, it is an oscillation, but this oscillation results in a stable, very small range. You see, and gets finally the temperature of the fuel gets very slowly increasing. You saw it in the lecture material. You remember in your slide 2. You remember here. I hope you see it before stopping. You see here, this figure. Remember, then we discussed about it. I hope you see it. You see here, again, for reactivity jump, like your case, 0.4, without no feedback, that means neutron kinetic, you have such very fast increase kinetic. And in case of dynamics, what we did in the last step, you see the power goes to maximum and then goes down and slightly oscillated and then gets stabilized. We don't have unlimited rise of the power. Exactly, you see that in last case, 0.4. But by plotting it, we should be taken into account again the time steps and then range what you have. Good. By plotting again, take please the text line out. Yeah. If you have any question, any comments, you can write email, ask via email, and if you have any comment today, I am available. Otherwise, then I would like to stop for today and have a nice day. Day is over, but your report again. Some pages and can be delivered during the this week or next week, by latest. Yeah, good. And I would like to say take care and see you next week. We're going to start with completely new aspect. Bye. Yeah, Mr. Moore, please.